Hi, I'm Chandramauli, the TA for this course. So today we'll be discussing some problems related to spontaneity of any given process, thermodynamic process, and something related to Maxwell relations and thermodynamic variables and all. So we'll do all these questions. So first, let me share my screen. Okay, is my screen visible?
Yes, sir.
Okay. So before we start solving some of the questions, I want to just revise a few things before going there because these would be necessary. Okay. So first, I want you to tell me some of the. Did you go through the lectures in the first place?
No, sir. This video because now my exam is spontaneous, so I cannot see the video lecture in this week.
Okay. Okay. So then I'll go through some of the things so that it's quite easy to solve all the problems because if you have not gone through the lectures, it will be difficult to solve these problems that we are going to discuss today. Okay. So first, do you know about the fundamental equations in thermodynamics? Do you know fundamental equations, Jaideep? Yes. Give me a moment, just some. Okay. So, do you know the fundamental equations of thermodynamics that was taught? What are the variables related to entropy, internal energy, enthalpy, all those things? Jaideep?
Yes, sir.
Okay, so you tell me as we go along. Okay, so if we see fundamental equations, okay, just a moment, just a moment. I think it's a little bit of problem. Okay, fundamental equations. So first we'll talk about internal energy. So internal energy is a variable of what? What are the variables of
You.
internal energy? U, yeah. What are the variables? What does it depend on? Number of particles, then entropy, and then volume. All right. So throughout the discussion, we'll be talking only about single particles. So we can ignore the n part. Okay. For now, we'll just consider it to be a fundamental equation with entropy and volume as the variables. Okay. So in that case, how do you write the total differential? So du is equal to du by dx, one variable, keep the volume constant, and dx plus del u by del v and keep entropy constant dv. Okay, so this is the total differential. Okay, now we know that du is equal to dq plus dw. Okay, which is equal to tds minus pdw. Okay, so now if you compare these two equations, we can easily tell that du by ds at constant V is going to be temperature, and similarly du by dV at constant entropy is going to be minus P. All right. So these are the quantities that we will get using internal energy. So why we are doing all these manipulations of different thermodynamics variable is that we want to get certain terms like internal energy, entropy, which are not measurable experimentally by some quantities that are measurable experimentally. For instance, in any given system, you can measure temperature, pressure, volume, and all. So then, based on these values, we can actually get to know about the change in internal energy, change in entropy as a result. So that's the whole idea of doing all these manipulations that we are going to talk about. Fine. So you get this part, right?
Yeah.
So now we go to enthalpy next. So what are the natural variables of enthalpy? Leave n out of it. So it is S and P, entropy and pressure. So because of that, we can write the total differential dH as del H by del S, keep pressure constant, ds, del H by del P, keep entropy constant, dP. Okay. So now dH, if you see, does what? du, what is the formula for enthalpy? U plus PV, right? Correct. So du plus PdV plus VdP. So now what is du? du is nothing but TdS minus PdV. Okay, plus PdV plus VdP. So now these two can get cancelled. So therefore dH is equal to TdS plus VdP. Again, what we are going to do is we are going to compare this equation, the dH equation, and this equation. Then if we compare that, del H by del S at constant P is again going to be equal to what? What, Jerry? Compare these two equations. Yeah, T. Similarly, del H by del P at constant entropy is going to be equal to what? Sorry? Hello?
V.
Yeah, correct. You get the idea, right?
Yes, sir.
Okay. So now this is enthalpy. Sorry, this is enthalpy. Free energy, internal energy, enthalpy is over. Then next is Helmholtz free energy. You will know why I'm writing all these things later when we start solving the problems. What is the formula for Helmholtz free energy? First, A is equal to, what is the formula? U minus Ts. Okay. Hmm? You got this? Okay.
Yes.
So this is the definition for Helmholtz free energy. So this is again going to be, let's say I write dA, it's going to be equal to du minus TdS minus SdT. So what is du? TdS minus PdV minus TdS minus SdT. So this and this will get cancelled. So dA is equal to minus PdV minus PdV minus SdT. All right. So now we'll go below. So that is the, so now Helmholtz free energy is a natural variable of NVT. Okay. Therefore, we can write dA as dA by dV at constant temperature dt plus dA by dt at constant volume dt. Sorry, this is dV here. All right. So now in that case, If you compare, okay, if you compare above dA and the below dA, we can get few other things. So dA by dV at constant temperature is going to be equal to minus P. Okay. Similarly, dA by dt, correct, by constant V is going to be equal to minus S. Okay. Alright, Jadip, got the point?
Yes, sir.
Similarly, you can do for Gibbs free energy as well, and then we'll get few things from that. Gibbs free energy. Again, Gibbs free energy is a natural variable of NPT, then dg is equal to sorry, just a minute. dg is equal to dP constant temperature dP plus dg del g by del T constant pressure dt. So now, do you know the formula for Gibbs free energy? G is equal to H minus Ts. Okay, this is the formula for Gibbs free energy. Therefore, dg is equal to dH minus Ts minus S dt. So now we need to get dH as well. So from before, we can know, where is it? dH is somewhere here. dH is equal to TdS plus VdP. Okay, I'll just substitute that here. TdS plus VdP minus TdS minus SDT. So therefore dg is equal to VdP minus SDT. So again compare these two, we get certain quantities. Delta G by delta P at constant volume, sorry, temperature. Constant temperature is equal to volume. Delta G by delta T constant pressure is equal to minus S. So these are the things that we have now. So now I did all these things for solving the problems. Okay. So these are the prerequisites. So these quantities, right? I'll just underline these important quantities. These, similarly dA by dV, this, all these are important because all of these compare properties that can't be measured to properties that can be measured experimentally. So that is the idea. Now next thing is something called Maxwell relations. Again, those are useful. So I'll write all the Maxwell relations. So Maxwell relations, you go through the lecture when you have time. Basically, these are relations that you get from these fundamental equations. Okay, and then there are four equations. These are Maxwell relations. So these are the four relations. I'll just write them down. From each one of these four fundamental equations, you get these Maxwell relations. These are basically just second derivatives. P, this one, then dt by dv by del by v. Write it there. del V by del S by V, del T by del V by S, del All right. So then one more thing that we need are compressibility factors. So these are again experimentally measurable quantities. All right. So there are four compressibility factors that we will see. So one is isothermal expansion coefficient. Okay. That is alpha, that is equal to expansion, right? How the volume expands as temperature changes with a constant pressure. That is, this is isothermal expansion coefficient. Then we have compressibility, kappa T. That's kappa T. This is kappa T. This is called kappa T is isothermal compressibility. So it's there. So basically we are going to compress and see how the volume decreases as pressure increases at a constant temperature. Then we have the heat capacities, Cp and Cv. Cp is nothing but delta S, delta Tp, and also it's another quantity delta H by delta T, P, constant pressure. Cv is similar, it's just that it comes under constant volume. All right. So these are the relations that we need for now. So let's get started. Right. Let's get started. So what are they? So the first question is, what is the current Maxwell relation? So I wrote four equations. So from those four equations, we have to find out which of these matches that. Okay, fine. There is a easy way of doing it. Okay. So actually, sir taught this in class. So you consider this, the four variables that are S, P, T, V. You write like this. All right. So now what are we seeing here? Here there are two things with S and T as the variable. Okay. You see S and T, they are far away, so it cannot be, we cannot use them. V and T are nearby, so we can use them. So it goes like this. Okay. Let's first consider V and T. Fine, at constant pressure. So basically it is V T at constant pressure. So it goes like this. If it goes like that, what we do is to get the Maxwell relation based on these V, T and P, we have to come like that. Okay. So then let's say del V by del T at constant pressure is going to be then it's going to be equal to del S by del P at constant temperature. Okay. Since see this is going up but this is coming down, so therefore a negative sign has to be there. So this is the Maxwell relation. Okay, so now let's go up and check. So you see del V by del T at constant pressure is equal to minus del S by del P at constant T. You see where we have del V by del T, we have del T by del V, so which is inverse at constant S. So we it's not that. Here we have to see del V by here. del V by del T at constant pressure. This is exactly what we have. So negative sign is also there. Del S by del P at constant T. So it is del S by del P at constant T. Okay. So this is correct Maxwell relation. But here the option is wrong. Okay. This is wrong. Do you understand this, Jaydeep?
Yes, sir.
One more thing is, see, S and T are far away. They should be adjacent for you to equate them. So since they are far away, these two options are also not correct. So the only option left is this. That's correct actually. But let's see how the values come. Again, I'll do the same thing. S P V T. Now what do we have? SP at constant temperature. Oh, we actually have done it before only. You see, del S by del P, that's what we have at constant temperature, is equal to negative of minus del V by del T. Correct. So that is exactly what we have here. Yeah, I'll just write it again. Del P by del T equal to minus del V by del T constant pressure. So that's our answer. So it's simple once you learn this technique. Fine, just go through the lectures once so you'll understand that. Now next is, what is the thermodynamic relations? So what do we need here? We want del U by del V at constant temperature. Okay. So how can we get that? So what we want is del U by del V constant temperature is what we want. Okay. This is what we want. So how do we go about solving this? So what is U? First, let's see what U is. U is a natural variable of U, N, V, and S, entropy. So we can write du as T ds minus P dV. Okay, this follows from this. Du is equal to dq plus dw. dw is minus P dV and dq is TdS. So that's quite natural. So now we are going to differentiate this du with respect to V. Fine, at constant temperature. So we'll just do that. Du by dV, constant temperature. So here there are two variables, so we have to differentiate them separately. Okay. Now how are we going to differentiate them? This is going to be T. So it's simple. This is going to be ds. Okay. This is T del S by del V at constant temperature minus P del V by del V at constant temperature. This is just one. Okay, it's basically dV by dV. It's just one. So what do we have? We will end up with T into del S by del V at constant temperature minus P. So this is what we have, but we need this part ds by dV and something else, something that is measurable. So we need to check the Maxwell relations. Okay. So now let's check. We need SP TV, right? We need S, V, and T. So basically it is this. So that means it's going to be something like this. So then from Maxwell relations, I'll just write this. I'll keep this as 1. So using Maxwell relations, del u, sorry, see del s, s v, you see del s by del v at constant temperature is going to be equal to del p by del t at constant volume. Okay, del p at del t by at constant volume. So both of them are going below. So that means both negative, so they'll cancel. Fine. Now let's substitute this 2 in 1. So what I'll do is substitute 2 in 1. So if we substitute that, what we get? Del u by del v, del u by del v at constant temperature is going to be equal to T del P by del T constant volume minus P. So if you see here, let's see the options, minus P. So the fourth one is the correct answer. Del P by del TV. This is the correct answer. Okay. So okay, Jaydeep, just notice this final equation. Okay. If you notice this final equation, okay, you see the final equation. Internal energy is not something that is easily measurable. Okay. You see, del U is there. But in experiments, you can maintain the temperature. All right. You can change the volume and see the change in internal energy. On the right hand side, you see pressure, temperature, volume, pressure, temperature. All these are experimental measurables. So basically, using some experimental measurables, we can get the value of internal energy using different experiments. So that is the beauty of these kind of thermodynamic relations and variables. Fine. You understand this point?
Yes, sir.
See, even if you don't understand, the complexities and all, it's fine. But you understand the idea behind it. We do all these complex things to come at some experimental measurable variables like volume, pressure, and temperature, so that we can get the free energy. Okay. So now let's go to the third question. So this question, yeah, this is actually a little bit easy only. Do you know the formula for, do you remember the formula for CV? T
That's
del S by del T at constant volume, right? This is the correct formula. Let's go back and check.
yes.
Where is it? Maxwell. Yeah, CV. Yeah, correct. That's the formula. Okay. So that is the CV. Fine. We need something like this. So which implies del S by del T at constant volume is going to be equal to CV by temperature. So if you see here on the right hand side, everything is in terms of Helmholtz free energy. So now we need something that connects Helmholtz free energy with this entropy. So how do we do that? We'll go back and check our formula. We'll go to Helmholtz free energy. See Helmholtz free energy, del A by del T at constant volume is minus S. Okay. So we'll use this formula. Fine. So we know del A by del T, right? Yeah. At constant volume is equal to minus S. So now we need del S by del T at constant volume, right? So what we are going to do is we are going to just differentiate it with respect to T at constant volume. Okay, first we'll do that on the left hand side. Del, okay, del S by del T at constant volume. You see here also it's T and constant volume. So it's just become del square A by del T square at constant volume. All right. So now what we will do is this value is equal to Cv by T. We'll just substitute that. So minus Cv by T. All right. So now we need, what do we need? We just need the Cv value. So Cv is equal to minus T del square A by del T square constant constant volume. Fine. So that is our final answer. You see, where is it? Del T square A constant volume. Yeah. So this is the final answer. Third is the second option is the correct answer. Okay. So now we can go to the fourth question. Did you understand this part, David?
Yes, sir.
It's simple, okay? Okay. Now, again, it's like a little bit tricky, but you think about it and tell me how we can solve this. We want CV. So again, I'll remind you, CV value, CV is equal to T del S by del T at constant volume. So we need to, kind of convert this del S by del T. Sorry, we have to get this del S by del T in some of these equations. So what we'll do is we'll consider first. We'll consider these equations first. We'll take this equation. Del P del P by del T V del V by del T. Yes. Okay, we'll consider this equation. So now what I'm going to do is we'll go and search, is there any equation that relates V and T, this del V del T S to del S by del T. Okay, we'll go and check that. Somewhere in Maxwell relations it might be there. Del V by del T, right? Del V by del T. See here, del V by del T at constant pressure is equal to del S by del P at constant temperature. It's there. So we are going to use Maxwell relations. So let's not let's not worry too much. I'll write it from scratch, okay? Again, consider this S, P, T, V. What do we need? We need V, T, S. Okay. Huh. So let me see this. Let's do this. V, T, S. It's not natural, but still we'll do it. Let's say we want this. And so what we'll have to do is We have to go like this and something like that. So it's going to be del T by del V, and S is equal to, it's going to be minus because this is going up, that's coming down. It's going to be minus B S uh, del P by del S at constant volume. Okay. Now we need del T by del S, right? So we just need to invert it. So reciprocal of that, not invert. S is equal to minus del S by del P at constant volume. Okay. So that's what we are going to do here. What we'll do is just write a little bit below. So T into, this will remain the same, del P by del T constant V. It's going to be minus del S. I'll just put the minus here. Minus del S by del P into V. So both are constant volume, so we can do this. C del P del S divided by del T del P. Okay, so I can just do this. Minus T del, of course, constant volume, del S by del T at constant volume. So what is this? Del S by del T at constant volume, you see here, it is CV by T, right? CV by
Yeah.
T. So it's going to be minus T into CV by T. So the final answer, it is going to be equal to minus CV. Okay. So that is indeed here. So this is the second option is the correct one. Okay. Got the idea?
Yes, sir.
So whatever the relations are, you try to see if there's some matching relations in thermodynamic, in the Maxwell relations or other things that we know, and then we'll go ahead from there. All right. Fine. So the fifth question is little bit tricky because we have not gone through the lecture. So there is a method called Jacobian. So that's what we have to use here. So do you know Jacobian? Did you study in your course in Max? Yes, Jerry?
No, sir.
Okay. Hmm, then this will be little bit difficult. How do we say? So basically, it is something like this, okay? Basically, you might have studied this in 12th maths. Let's say we have two equations, huh? Let's say we have equation 1 is u is equal to, let's say it's an equation in two variable, okay? A1, let's say I'll put it as a1x plus a2y. Then we have second equation a, not, I'll put it as b1x plus b2y. Do you know how we write this in matrix form? Okay, remember that. Mm, do you remember that, Jaydeep? We write something like this, then a1 a2 b1 b2, then x y. You remember this? In school we used to write this 12th marks.
Yes, sir.
So So when this a1, a2, b1, b2, they are all the slopes or derivatives of these functions by keeping x and y constant. Okay, let's say we'll do something like this. I'll tell when it's a Jacobian. Let's say you make it like this, u, v, or else I'll make it when it becomes something like this. So du by d. Okay. So thing is, we'll start writing it as a total differential. Fine. So what we are going to do here is, let's say you see du dv. Okay. Then we write du by dx at constant y, du by dy at constant x, du, sorry, now it's v now, dv by dx at constant y, dv by dy at constant x. Here it becomes dx and dy. Okay. So when you write this, write a total differential in this form, then these two, this is a vector. This is called Jacobian matrix. Okay, and this is again a vector. Okay, so this is the Jacobian matrix. When you take the determinant of it, determinant of Jacobian is basically determinant of Jacobian matrix. Okay, Jacobian is equal to determinant of Jacobian matrix. Okay, so we are going to use Jacobian and some relations of Jacobian. Okay, so we want to do. There are some rules related to Jacobian. You go through the lectures to understand the rules. For now, I'll solve the problem. Once you go through the lecture related to Jacobian and all, then you'll understand. Okay, it is just 2 lectures. You just go through it, you'll understand. Now the question is, what is the question? Forgot the question. Correct thermodynamic. Okay. There, what is del P by del T is equal to V at constant V. What is the value? Is what they're asking. Okay, let's see. So what we need to find, del P by del T at constant volume is one we need to find. Okay. So in Jacobian transformations, what we do is first we write it like this at constant V. So basically, so this is a function of P and V, and this is also a function of T and V. Okay. Now we need to transform it. So generally for transformations, what we do is we multiply and divide by, do it step by step, pt. Okay, so you see I'm multiplying and dividing by pt. Okay, pt here, del pt here, and then I'm taking the del tv there. All right, so now next what I do is, so since these are determinants, I told you, right, these are Jacobians, so they are determinants. So when pt they become tp, it becomes negative. PV, when it becomes VP, then again becomes negative. Negative will get cancelled. Okay, I'll just write it step by step. Come, that we don't miss any step. PP. Okay, So it's simple. Negative and negative will get cancelled. Into, now we want t on one side, right? So I'll tell you why we need t on one side. Del Vt. So when this is like this, when it's written like this, Pt and Vt, then we can shift it to a form like this. Del Pt by at constant, del P by del T at constant V. That's the idea of doing this. Now what this becomes is, this can be written as del V by del T. V is numerator, T is denominator at constant pressure. Okay. Into minus. Now into minus del P by del V del at constant temperature. So what is this? Del P by del T now? Del P by del T constant volume. Okay, let me keep this as 1. Now if I keep that as 1, now what are these things? First, okay, we know certain things. We know isothermal not isothermal, expansion coefficient is 1 by V del V by del T at constant pressure. So this is known already. So you see here del V by del T is already there. So which implies del V by del T at constant pressure is equal to alpha V. So this expansion coefficient and volume are measurables, right? So we have this. Then similarly we need isothermal compressibility test del V by del P at constant temperature. So which shows del V by del P at constant temperature is equal to what? Minus KTV. But what we want del P by del V, right? So just reciprocal of that. Del P by del V at constant temperature is equal to minus 1 by KTV. So we have these two things. I'll just write this as 2 and this as 3. We'll substitute 2 and 3 in 1. Now let's substitute. Now 2 and 3 in 1, right? 3 in 1. So del P by del T at constant volume is equal to alpha V into minus 1 by KT into, oh, that is also minus, no, there is 2 minus. Already on minus is there, I'll put that minus KTV. So that is equal to VV will get cancelled. So it's equal to alpha by KT. So that is the final answer. Okay, we'll see here. Do we have alpha and alpha by KT? Yeah, third one. That is our answer. Okay, so alpha is an experimentally measurable quantity and KT is also an experimentally measurable quantity. So these are the things we can do. Okay, did you understand this, Didi? Any doubt?
No, sir.
All right. So now let's come to the sixth problem, where we have to find out whether a given set of variables lead to spontaneous process or not. So what is the formula that we are going to use here? Delta H and delta S. What is Gibbs free energy? What is the formula for a Gibbs free energy change? What is delta G is equal to? Delta H naught del minus T delta
Yes.
S naught. Correct. This is the formula, right?
Yes, sir.
Okay. And what is the condition for spontaneity? Tell when a condition is spontaneous, when a process is spontaneous, when delta G is less than 0 or greater than 0. Jaydeep, less than 0 or greater than 0?
Greater than 0.
No, delta G has to be less than 0. It has to be negative for a spontaneous process. Okay.
Yes.
Okay. So we have 4 conditions. Let's check one by one. Basically, they're asking which set of reaction will occur only at higher temperature. Okay. So let's check. Okay, let's first do for D. Okay. D, what is D delta H is delta G not D, I'll put delta H not D is 0 minus some temperature into 30 kilojoules. Okay, I'll just put, so it's going to be minus 30 T. So here you see what temperature can never be negative, right? So whatever the temperature is, this for all T, for here for all T, delta G not D is going to be less than 0. That means it's going to be spontaneous for all temperature. So this is not the answer. Okay, for all T, they are asking the reaction which is spontaneous only at higher temperature. Fine, we have to find out condition like this. Then we'll go to condition C. What is the value here? Delta H is 50 kilojoules and delta S is minus 10. Let's see. Delta G naught C 50 kilojoules. 50 kilo, I'll just put 50 into 10 power 3. I'll just make it joules, okay? Into joules minus T and minus 10 joules per Kelvin. Fine. So this is going to be 50 into 10 power 3 plus 10T. This is it'll be in joules. Okay. So will this condition be ever spontaneous? Huh? For any T, delta G naught C is going to be what? Less than 0 or greater than 0? For everything, there is no negative value at all here. Okay. So it will be always greater than 0. So not never spontaneous. Okay. Do you understand this, Jaydeep?
Yes, sir.
So basically, this is what you have to do. You have to calculate like this. Okay. Then we'll go to B. Problem B. B is now delta H naught. What is delta H naught added? What is B? Plus minus 50 minus this. Okay, minus 50 kilojoules minus 50 kilojoules delta S naught is equal to minus 10 joules per Kelvin. So now let's see, delta G naught B is equal to minus 50 into 10 power into 3 minus T into minus 10. Okay, so minus 50 into 10 power 3 plus 10T. So this is the delta GV. Okay. Now we need to find out whether it is spontaneous at higher temperatures or lower temperatures. So the condition for spontaneity is, for spontaneity, delta GB naught should be less than 0. Correct.
Yes, sir.
So what I'm going to do is minus 50 into 10 power 3 plus 10T. I'm just substituting. Okay. It's going to be equal to less. I'll just put. We have to find the temperature now. So what we are going to do, we'll add this on both sides. 10t will be less than or equal to 50 into 10 power 3. So then divide by 10, 5 into 10 power 3. So basically, this should be less than 5000 Kelvin for this process to be spontaneous. So that means what? It is spontaneous at lower temperature, not at a higher temperature. So again, this can't be our answer. Okay. So the last thing is last process will set delta H naught is equal to 50 kilojoules. Delta S naught is equal to 10 joules per Kelvin. Let's check. Both are positive, no? Yeah, both are positive. Let's check. Now again, I'm just going to calculate delta G A is equal to 50 to 10 power 3 plus, no, minus 10t. So this is what is going to be. Now let's equate this to less than 0 and then we'll see. It's 10t less than 0. So minus 10t minus. So we need to multiply by minus 1 on both sides. So when we multiply minus 1 on both sides, the sign is going to get changed, right? So it will be like this. You understand, right? So then we have to reduce this further. If we reduce this further, it's simple. T should be greater than 5 into 10 power 3. So which means T should be greater than 5000 Kelvin. So this is the condition at which only at higher temperature, A is a condition where only at higher temperature the reaction will occur spontaneous. That's what they're asking. For which set of delta H and delta S will reaction be spontaneous only at high temperature? So A is the answer here. Okay. So like this, you will have to evaluate for the question in the assignment problem. Fine. Understood this, JD? Hello.
Yes, sir.
Okay. Now this question. How do we find this answer? We need Cp. We need to find del Cp by del P at constant temperature. Okay, let's start working on this. So what is Cp? Do you remember that? Remember it is T del S by
Del S divided by del P.
at constant pressure. Correct. All right. So now what we need is del Cp by del P at constant temperature. Correct. This is what we need. So we need to just evaluate this. So we can do it in parts, like keep del S by del T at constant P constant, then del T by del P at constant temperature, because we are differentiating with respect to temperature, right? But so this is constant temperature, that means there's not going to be any change, so this will be 0, right? So this entire term is going to be 0 because this quantity is 0, plus T into del S del T at constant pressure, and then do del by del P at, okay, at constant temperature. So since this is a state variable, since entropy is a state variable, we can write the above equation like this, is equal to del square S by del P del T. Okay, we can write it like this, and then we can further manipulate it as follows. I'll take del T outside and then put del S by del P constant temperature. All right. So then what happens? We need to use Maxwell relation now. So what is the Maxwell relation? Remember we did this before. Let me just go back. Del S by del P at constant temperature. Okay. I'll go somewhere here. If we go here, Maxwell relation. Del S by del P, right? Del S by del P. Where is it? Yeah. Del S by del P at constant temperature is minus del V by del T at constant pressure. So we'll just substitute that here. Yeah, I forgot this pressure. So we are substituting the Maxwell relation. So it is del S by del T into del V by del T at constant pressure. Again, another constant pressure over here. So both are constant pressures and both are del T's. So what it will become is, and there was a minus sign. Okay, this minus. So then this will become minus T del square V by del T square constant pressure. So that is the value of del Cp by del P at constant temperature. So this is the answer for the question. Fine. What do we have this here, right? This is the answer. Okay. Understood this? Just manipulate it and then use Maxwell relation. Simple. Okay, Jaideep?
Yes, sir.
Okay. So this question, next is we have to evaluate this particular quantity. There are two ways to do it. One is the easy way, and there is another difficult way also. First, I'll tell the easy way. So this is
Sir,
simple.
it is the cyclic rule, I think, right?
Exactly. That's the easy way. Yeah. So if you know that, then we can just skip this, okay? So it's just use cyclic rule. Correct. So what's the answer?
-1.
Correct. So basically cyclic rule is something like this, right? Z del Z by del what? Huh? Yeah. Oh, sorry. Del Y by del Z. Huh? Del Y by del Z. What am I doing? Correct, right? Or no? Yeah. Del Z by finally del Z by del X. Yeah. Correct. So that's all. So it's a cyclic rule. So the answer is 0. Sorry, -1. Simple. Okay. In that case, we will go to the, I think that's it from my side. I will tell some, I mean, you are asking some more questions, right? Just check once. Let's check. No. Top. Yeah. So you were asking question 1. Okay. Question 1 is like directly from class actually. I'm not able to share. Okay, let me share the entire screen. Okay, so you can see my screen, right? So as you can see here, see the first question is quite simple. This is directly from definitions given in class, where delta G is a natural variable of temperature and pressure, not volume. So this is not correct. And Helmholtz free energy is a natural variable of temperature and volume, not pressure. So again, this is not correct. Entropy, that time you need volume, not pressure. So again, this is not correct. This is natural variable of U is S and V. So this is the correct answer. Fine. Okay, Jaydeep.
Yes.
You had what are the questions? 1,
1, 5, and 7.
5 and 7. Okay, so 5 is again a definition. So delta G is the non-PV work that a system can perform at a constant pressure. While delta A, Helmholtz free energy, right? That is the PV work. That is the mechanical work. Delta G is the non-mechanical work. Fine. And then 7, of course, I discussed in the,
Yes, sir.
yeah. Let me stop presenting. Okay, so that's it, I guess. Do you have any other questions?
No, sir.
All right. If that's the thing, we'll close the session. Fine.
Okay, sir. Thank you.
Okay. See you. Thank you.